Okay, so geometric series part 1. I'll just take you through some very quick worked examples. We've noticed already that there are two versions of the formula for a geometric series. We tend to use the one on the left if the absolute value of r is greater than 1. That means if the common ratio is between -1 and 1, you would use this one, otherwise use this one. Okay? So you just need to remember that. It's not fatal if you use that formula all the time. It just means that in some situations you will end up with awkward negatives to deal with, and we try to reduce that where possible. Okay, so to our first example, probably the easiest one known to mankind, find the sum of the first 10 terms in the series 2 plus 4 plus 8. Okay, let's note down firstly that a in this series is equal to 2. 2, sure is. The first term is equal to 2. And the common ratio is 2 as well. So the common ratio is equal to any term, so I'm taking the second one, divided by its previous term. Yes, that comes to 2. And here, the value of n is 10. Because we are finding the sum of the first 10 terms. Okay? So now let's have a look at this. The common ratio is 2. It's greater than 1. That's the important point. So we're going to use this version of the formula here because r is greater than 1. And by simple substitution, we can say the sum of the first 10 terms is equal to a, which is 2, r is also 2, to the power of 10 minus 1, all over 2 minus 1. I'm liking that because we've got 1 on the bottom, on the denominator, so that's going to make it easier. So the sum of the first 10 terms is equal to 2. 2 to the power of 10 is 1024, so and subtract 1, you've got 1023. So now all that's we need to do is multiply 1023 by 2 and we'll get 2046. Okay? Therefore S10 equals 2046. Okay, to our second problem. Find the sum of the first 8 terms for this series. Alright, let's note down our values for A, R and N, and then it should be a case of selecting the right version of the formula and substituting into that formula. So here A is a third. R is 1/6 divided by 1/3. As I've pointed out in the past, if you're dividing something by a third, it's the same as timesing that thing by 3. So you're going to find that R is equal to a half. And here, the value of N is given there. Okay, we're finding the sum of the first 8 terms, so N is equal to 8. Alright, here we notice that R is between -1 and 1, so we're going to use this version of the formula. Sn equals a 1 minus r to the n over 1 minus r. Now all we need to do is substitute, then simplify and see what we come up with. So sum of the 8 terms is equal to, a is equal to a third, 1 minus r is a half. Should have used square brackets there because I'm going to need rounded brackets here. A half to the power of 8, close off with square brackets, and what have I got here? I've got 1 minus a half, which is a half. Okay? Now, one thing that's going to speed things up a bit is if we notice that if we're dividing something by a half, another way of thinking about that is timesing that thing by 2. Alright, so we can say S8, now 2 lots of 1/3 is 2/3. So that's going to help us out a bit. And I don't need square brackets. So 1 minus Now, 2 to the power of 8 is 256, isn't it? Now, remember this index law here? This is useful stuff. 1 to the power of 8 is 1, so that's nice. And 2 to the power of 8 is 256. Okay? Now, yes, sure, you could go to your calculator and evaluate that, but let's use a bit of common sense before we use our calculator. And let's say S8 is equal to 2/3. I want to express this in terms of 256. Okay, so 1 can be written as that, can't it? Anything divided by itself is equal to 1. Okay, so 1 on 256. Whoops. Okay, and so S8 will equal 2/3. Same denominator, I can just do this. 255 over 256. And I think your answer is going to come to 85 on 128. Okay, your calculator, if you put that in, your calculator will probably give you some awkward decimal value. It's better to write it as a fraction there where possible. Sometimes it's not. In this case it is. The reason being, that's what we call an exact value. Otherwise you're liable to get some sort of decimalised approximation. Okay, can we stop there please?